We're beginning a new symposium series to feature the work of faculty in the department. The flyer nicely captures the goal of the series to learn about a specific research topic, the scholarship of the faculty, and the process of social science research. When people speak about their work, it comes alive, it brings depth and understanding. And let me thank too Professor Amy Traver, Professor Mark Zeltzer for organizing the symposium and for the work they did. And Professor Patrick Byers will begin the series with a very intriguing title to his talk, What Could a Robot Know About the Discovery of the Mind and Language? And I look forward to hearing much more. So once again, let me welcome everyone. Thank you for coming and enjoy the presentation. And now, Professor Zeltzer, you can introduce Patrick. Thank you.
Hi, thanks so much for introducing the series. Yeah, we're really excited about it. I'm Mark Zeltzer. I'm here introducing the speaker. For those of you who, like me, don't know him, Dr. Patrick Byers is currently assistant professor of psychology at Queensborough. Right, so he earned a BA at Clark University in Worcester, Massachusetts, and a PhD at the CUNY Graduate Center, where I did. Patrick's been teaching in CUNY colleges since 2012. And beside teaching, he's also done research for the Department of Education in children's cognitive development and children's media. Dr. Byers' recent research has focused on language use, right? His dissertation focused on the conditions in which someone could be meaningfully said to know something. Okay, his most recent work, and what appears to be the subject of his talk, has studied the ways in which mentalistic terms, such as attitude, belief, desire, are used both in psychology and in stories to make sense of people's behavior. So it looks like there'll be lots of interesting overlap with the philosophical questions that epistemologists have been asking lately, stuff that I'm interested in and I'm really looking forward to. So without further ado, I present Patrick Byers. What could a robot know about the discovery of mind and language?
Thank you. Thanks a lot, Mark and Amy, and for everyone for having me here. All right, so this is actually, what I'm going to talk about is work that I did last year and have just had a paper published on, and kind of combines some of what I did with my dissertation and then a recent topic in the study of artificial intelligence and the development of artificial intelligence. So there's a lot to cover here. So I'm going to get right into it. The first concept I want to introduce is what's called an artificial neural network. And this is a currently very popular form of artificial intelligence. And it's, in simple terms, it's like a very simplified, emphasis on very, version of the nervous system. So really, it's like the nervous system in certain general respects. So there's a set of interconnected nodes, as you can see, the red, blue, and green circles. And these are sort of like neurons, in a sense, and they're connected to one another. They can send and receive signals. And you can see on the left, an array of input nodes, and then on the right, the output nodes. And this essentially corresponds to in the nervous system, your senses, like the retinal neurons in your eyes, your other sensory neurons. And then those are fed into the nervous system. And then there's the output, like the motor neurons that move your muscles, allow you to talk and do things, etc. So just in certain general ways, an artificial neural network is like the nervous system. And basically the way that they work is it's a form of artificial intelligence, and it can perform like categorization or translation tasks. So this next image here provides, I think, a useful illustration of how it might work, how one might work. You could have a neural network where you feed in images of animals, you can see here on the left, and then the signal is then processed, then the output, the system tells you which animal it is. Now, you might ask, looking at this, like, how does this work? Does someone just go and tinker with each connection? It seems very tedious. The beauty of it is, initially, when you start off, you just have a computer simulate the network doesn't work. You put in a picture of a lion, it tells you, gives you a random answer. The way that the network is developed is through what's called training. There's some kind of algorithm that that automatically adjusts the weights between the nodes in a way that very gradually leads to getting the correct output for a given input. So it's kind of like the process of evolution by natural selection. It's like very, very gradually, randomly trying out tons of possibilities. And I can't tell if that was a question or not, but do feel free to jump in. Basically, the way that it works is the algorithm will gradually bring the system towards a state where you get a useful output. You get the output that you want for a given input. So you start off with a system that does not tell you which animal it's being shown. You feed it tons and tons of what are called training images or the training data. Then eventually, after this computer runs nonstop for hours and hours, maybe days,
That's not a class, that's like a book.
you get a system that gives you the correct output for a given input. So this could be done for like the interpretation of images. And you see this online now. If you upload a picture and you're told automatically like image of, family in a canoe. This is using a neural network. They're also used for translation. So you can develop one where the input is some sample of text in one language, and then the network is trained to give you as the output, the translation in another language. So again, let me know if there's any questions on this basic concept. But I sort of talked over the video I was going to show. But it's for our purposes, we're only concerned with like the basic things that these networks do. And they're relevant. The reason why they're relevant and so popular now is that they can do a lot of things that artificial intelligence was previously not able to do. So to give sort of a very brief history, in the early days of artificial intelligence in the mid 20th century, there was a lot of enthusiasm because the researchers developing robots and other systems they thought that they were genuinely just a couple of years away from replicating all human abilities, cognitive abilities. And this was because they were very quickly able to do things like design a system that could play chess. And it's kind of a funny history. In their mind, they were like, well, chess is the most sophisticated thing a person could possibly do. So if we're automating that, we must be done. We must be almost done. What they discovered, though, was that seemingly mundane things that people do are almost impossible to formalize and to make a traditional computer carry out. So if you think of like, the best example would be like a casual conversation that we might have if we were at Queensborough. You meet someone in the hallway, you start talking. People can have interactions like this. Computers can't. There's no set of like rules that a computer can follow that will appropriately guide it in having a human-like casual conversation. So they can play chess, they can do more complex analytical things, but these everyday activities are difficult, as are things like image recognition. So what artificial neural networks have allowed us to do is not replicate casual conversations, but to do things like image identification, visual identification, translation, other tasks that we have not been able to like reduce to a set of rules that we can program a computer to do. So in recent years, the neural networks have shown kind of very impressive abilities. There was one case where, I believe this was in New York a few years ago, where there's a neural network that had been designed to, basically it was fed in information on patients from a hospital or healthcare system. And then the diagnoses that the patients went on to have. And they trained the system to try to anticipate what a patient was going to be diagnosed with. And it was found, interestingly, especially for the psychology department, that this system was able to predict people who had developed schizophrenia before a doctor was able to make the prediction. So, interesting finding in general, but also what this raised was the question of, well, it's great that we have a computer that does this, but we would seem to benefit us if we could know like how it's doing this. How does it know that the person is likely to develop schizophrenia? How is it reaching this conclusion? So this has led to the need, or to the push, for what's called explainable AI, which are neural networks that can not just do what they normally do, but explain why they do what they do, why they reached a particular decision. So this would involve like the neural network reporting what it like thinks or believes to be the case, what it was trying to do, its attitudes towards certain things, the way that we explain human behavior, what I believe, what my attitudes are, what I want. The other reason for explainable artificial intelligence, or XAI, as it's abbreviated, is that neural networks are not flawless. Although they can work very impressively, they sometimes make bizarre errors that are kind of alarming. And if you read about them, you experience a lot of caution in your desire to let these things do things for you. One really relevant and interesting example was kind of similar to the previous example and I think it was also in New York. There was a neural network that was trained to automate the process of like allocating resources at a hospital. So based on, it was fed information on like patients who came in, what their condition was, other characteristics of them, and then their outcomes. The goal was for the machine to say, this to automate the process of deciding what to do for a given patient to make the best use of resources. And although the system came to, do this to a decent extent, it made this awful error. What it did was, for patients who had pneumonia, the system recommended that pneumonia patients who also have asthma should be, given less attention. And patients who don't have asthma and have pneumonia the doctor should spend more time focusing on them. Which the doctors saw this and they're like, that's ridiculous. If you have pneumonia and asthma, you're at much higher risk. You need like serious attention. The error that the network had made was that because people with pneumonia who also have asthma, because they're so much at risk, they're given urgent attention, they tend to recover very quickly because they're treated so urgently. So the kind of reasons for why the doctors were doing what they do that were reflected in patterns in the data weren't understood by the network, and it made this recommendation or decision that didn't make any kind of sense. And this is an important example. I think it's not just interesting, but it shows kind of alarmingly how if you had a system making decisions like this and you didn't already know why you would want to make a certain decision, or you didn't understand the basis, the context in which the system was making the decision, or the grounds in which it was making the decision, you wouldn't know that there was the error. It was only because the doctors could understand, oh yeah, the system's seeing the fast recovery times for the asthma plus pneumonia patients and misinterpreting, it's not aware of what that means. So this, again, is another reason why we would want explainable artificial intelligence, a system that can explain why it did, what it was trying to do, what it thought was the case, and so forth. Because it won't always be the case that we'll have the understanding that we have of the situation in the pneumonia and asthma example. So this is where I think there's a link to work that I began with my dissertation, this push for explainable artificial intelligence. Really beginning in I think 2017, 2018, it really was like a major thing and continues to be in artificial intelligence, this attempts to design systems that can report like what they think, what they're trying to do, and so forth. I think there's a lot of complexity here and a lot of issues that are being skipped over and are going to complicate this attempt to develop explainable artificial intelligence. So to explain this, which I can do, but not the computer. To explain this, I want to now turn to the work that I began with my dissertation, which is focused on what I'm calling knowledge claims. So a knowledge claim, this is a distinction or sort of a category I came up with. A knowledge claim is any like ascription of knowledge to someone. So if you say that someone knows that X, or knows how to do something, or someone grasps some concept or grasps some principle, all of these would be knowledge claims. For people in philosophy, maybe you're familiar with the like knowing that versus knowing how distinction. In this approach, both of those are knowledge claims. So what I looked at and what I've been looking at in this research is, what are these knowledge claims? What are we doing when we say that someone knows something? And the way I did this was by studying in first texts of research articles, actually, on children's cognitive development. I looked at what researchers claimed that children knew and the reasons that they gave to support those claims. The goal being trying to understand, like, what does it mean to say that someone knows something? And my hope was that by studying the ways people make knowledge claims, I could get a different understanding of, or better understanding of, what is being done, what these claims mean. So this involved a lot of in-depth analysis, which I'm showing some of right here, of research articles, taking out the knowledge claims, taking out the reasons that were given to justify their assertion, to justify them being contested, etc. It's not coding. It was just really like setting everything out to try to look for overall patterns. Not going to go into the nitty gritty of this. The ultimate goal was to develop like a general model of, when we say someone knows something, has a concept of something, grasps something, what does this mean? What are these claims about? So the basic conclusion that I reached was that knowledge claims are descriptions of behavior, specifically behavioral capacities. They're descriptions of what a person can do, rather than descriptions of like content in someone's mind, for example. And for the sake of time, I won't go into the relevance of this in cognitive psychology. But again, I just want to explain what I mean when I say knowledge claims are descriptions of behavioral dispositions, or sorry, dispositions or capacities. Let me just make a note here. I go back and forth from one word to the other. So if I say disposition, not capacity, it's just trying to say capacity now. A behavioral capacity is basically someone's ability to do something. So for example, we could say that a person knows the word Gesundheit and knows to say that when someone sneezes, the German thing you say after someone sneezes. So that would be a behavioral capacity. They are able to do this. And what I want to point out is we can describe capacities at different levels of generality. We can talk of very narrow specific capacities, like, being able to tie your shoes, being able to brush your teeth. We can also talk of more general capacities. So we could say that the person has the capacity to speak German fluently. So this is a much more broad capacity, right? Whereas, like, to focus on these two examples on the screen, whereas the narrower one, saying Gesundheit, is just saying one word in one type of situation. The broader capacity of being fluent in German involves saying all sorts of different things in all sorts of different situations. So it's a very broad capacity. Another thing to point out, two more things I want to point out with this, is the very broad capacity subsumes, in this case, this particular narrower capacity. If we say that someone is fluent in German, this would imply, we would expect that they would say Gesundheit or could say Gesundheit when someone sneezes, right? Because this narrower capacity is an instance of the broader capacity. Now, when we get to claims about like concepts that a person knows, principles that they grasp. Again, what I found was that these two are best explained as just very general behavioral capacities. They don't look like behavioral capacities, but this is only because they're so general that what they subsume is so heterogeneous that it doesn't, look like anything particular. But my claim is that if you say that someone has a concept of number or a concept of object permanence, that this is just a description of how they act, how they can be expected to act. It doesn't seem like a description of behavior, but it's kind of sort of an okay analogy. You could say that it wouldn't make sense to say that a piece of furniture isn't an object because furniture doesn't look like anything in particular. A chair looks like something. Furniture doesn't look like any one thing in particular. It can look at all sorts of things are furniture. It doesn't follow from that pieces of furniture are not objects. So similarly, if we say that someone grasps the concept of a verb, it's a part of speech, this is still, it's just a very general description of their behavior. And it subsumes, or it's instantiated by more specific capacities, behavioral capacities. So if we say if someone grasps the concept of a verb, we could say that they should be able to, we expect them to be able to identify the verbs in a particular phrase or utterance, right? And then that capacity subsumes even more specific ones. So we could say that, a person answered ran when asked, what is the verb in the sentence, Jane ran to work? So they correctly answered that. That would be a very specific instance of this more general capacity in the middle, which itself is a more specific instance of this very general capacity. So we number these, I can illustrate how you can reach logical conclusions about them. So numbering them as 1, 2, and 3, 1 being the most general. If 1 is true, then it follows that 2 and 3 are true. On the other hand, if 3 is not true of someone can't do what's described in 3, then all other things being equal, they wouldn't be able to do they don't have the more general capacity in 2 or 1. Then finally, those are deductive. Then finally, the inductive inference, if someone can do 3, if 3 is true of someone, then 2 and 1 may, but not necessarily, may be true. Again, because induction is not definite. So this very extremely dry, hopefully not overly boring description here in terms of logic is reflected in how you might say if in the case of students taking a test, you might wonder, or you might hope that, do the students understand the material, or are they just memorizing the definitions and regurgitating what they've memorized on the test? Are their answers on the test a reflection of a more general capacity to talk coherently about some topic? Or is it a more narrow behavioral capacity? They can just say these things, you just know the definition, you can't really go beyond it. That's sort of the real world version of the limits to this induction here. We see that, the student answered the question correctly, but we ask, do they understand this more broadly, or is it just that they can answer this type of question in this particular way? Now, there's this is sort of the general structure, the general way that people make knowledge claims. There's by the way, a lot more evidence here, but in the interest of time, I'm going to skip over it. But I want to point out how, although these logical inferences are often made, we can think of examples of how they're made, there are also interesting exceptions. Specifically, although it's the case that if someone has one particular narrow capacity, we wouldn't say that they have necessarily a much more general ability based on that. In a lot of cases, like the example of students regurgitating things by rote that I just gave. On the other hand, in contrast to that, there are situations in which we see someone do one particular thing on one instance, and we say, all right, they must have this more general capacity. So to illustrate this with an example from like young children's uses of counting. Imagine we were trying to determine whether or not a child understands how counting works. Not just that they do it, but thinking of like 3-year-olds here. We're not just interested in, will they count, but like, do they understand the meaning of what they're doing? So imagine we give them a box with items on it. By the way, the items are on the box, not in the box, because it was too hard to make a box with items in it. So that's why they're on top of the box. So if we ask a child, we give them some items on top of a box, and we say, how many items are there on the box? In scenario 1, let's say they respond, they count them 1, 2, 3, 4, 5, 6, and tell us 6. Now, this would be consistent with the child understanding how counting works. This is the right answer, but we might argue that, they don't really have this broader capacity, this broader knowledge of how counting works. They just know to count when they're asked how many. So we might be suspicious and not want to make this inductive inference that they have more general conceptual knowledge. On the other hand, imagine if in a different scenario, you ask them the same question, but as they're counting, out of nowhere, another object falls into the box, and joins the other objects. And the child asks you, as they stop counting, they say, wait, do you want me to, should I also count this one that just fell in? Now, this would indicate much more, it would be much more likely, I think you would agree in this case, that this child really understands what they're doing. Specifically, note how we could say there's no other explanation for the child's behavior here in scenario 2, again shown here. There's no other explanation for this behavior besides that they know how counting works. Why would they know to stop and say, should I count this one? It would only make sense to do that if you knew how counting worked. By the way, I'm not making this argument. What I'm trying to bring up is the fact that it would be a reasonable and understandable and coherent thing to say. Whereas in the other scenario, we could say, maybe they understand, maybe they don't. Maybe it's just rote knowledge. In this case, we could, and in other cases, we could say, actually, they must have this more general knowledge because there's no other explanation for why they would have done this specific thing. So hopefully this makes sense. The fact that people can say there is no other explanation for this behavior. You see this in research articles on children's cognitive development. Here's one example. But it's also just a plausible thing that people could say. If you encounter someone and you start talking to them, you haven't heard all the things they can say, but you can conclude with certainty that they must not have just memorized this script by rote. They must be able to speak whatever language you're speaking to them in general. So we can confidently make these seemingly inductive inferences for some reason. I won't go into the reasons for the sake of time. What I want to point out is that the fact that people make knowledge claims in this way brings up problems for explainable artificial intelligence. It appears that our use of, when we claim that someone knows, believes something, has an attitude, desires something, which by the way, function in essentially the same way as knowledge claims. They're also descriptions of capacities. The problem is these are useful to make in social interactions with people because of assumptions that we have about the sorts of things that people can be expected to do, won't be expected to do. So if we say that someone, for example, like they can do long division or they understand long division, we wouldn't expect them to solve some kind of like insanely complicated problem like this. But on the other hand, as I was just mentioning, from seeing someone, in some cases, the performance of one specific behavior can lead us to confidently say, this person must have all these other abilities, this much more general capacity. I want to focus specifically on this second point and point to the challenges that it brings up for explainable artificial intelligence. The reason for this is that although we can make these inductive inferences safely or confidently with human beings, it would not appear that we can make them for neural networks, as the following examples show. I think these are pretty interesting examples. So here's the results of a neural network that was trained to recognize the content of images. So again, it was fed in hundreds of thousands of images, trained with the algorithm until it gave the correct output, the correct description of each image. And then we present it with new images and see, all right, let's see if it can interpret these images. And it does, usually, just like a person can learn to, describe a scene. But the issue is that whereas imagine you're talking to a child and you're wondering, does the child know what a car is? And you ask them, you're like, is that a car? Is that a car? You can pretty quickly get a sense of like whether or not they know this concept. And you could very safely anticipate when they're not going to apply it. But yet, as this example shows, neural networks will sometimes make totally bizarre, like kind of outrageous interpretations. In this case, the system interpreted this sign with stickers on it as a refrigerator filled with lots of food and drinks. So what this illustrates is if we were to have this network explain what it was doing, and it said it believed it was looking at a refrigerator, this would give us a completely misleading, almost useless description of what it was actually looking at. Where if a person says, I thought it was a refrigerator, it would have to have looked somewhat like a refrigerator. It wouldn't be that it was a pencil or something. But this is just one of many examples of this. The second example I want to give, which I think is even more interesting, you may be familiar with this game. Let me just actually show this here. This game from the 80s, Brick Breaker. It's basically like sort of like tennis. So you can see that you have like a paddle at the bottom, and you learn to bounce it up and knock the bricks out without the ball losing the ball. So a artificial neural network was trained to successfully play this game. Again, at first the paddle was moved randomly and it would quickly lose, but the algorithm updated how it worked and gradually came to play competently. And impressively, not only did it learn to play, but it optimized its playing. It was programmed to do this. So this is after 200 training episodes. So 200 iterations of updating the connection weights between the nodes. Then you get now a system that can play pretty well, right? This is obviously not random. This looks like a human playing. But then impressively, after 400 training episodes, something very interesting happened. The network actually learned to, maybe it's more than 400. The network devised this ingenious strategy. Let me fast forward to where it is. There we go. After 600 iterations, this really sophisticated strategy emerged. The system literally learned to make a tunnel on the left side here so that the ball would get stuck up there and very, very quickly win the game. So this is the type of thing, again, that like a human player might come up with, especially someone who plays a lot. And this is a perfect example of something, if you saw a person doing this consistently, you would say, well, that wasn't by chance. They must have, identified this as a strategy. In other words, it would be a perfect example of the situation where you'd say there's no other explanation for this. They must have come up with this strategy, right? For example, well, for the sake of time, I won't go into examples. But what was found was, although the system evolved this very sophisticated strategy, it was extremely fragile. or brittle, meaning that the strategy only appeared in this one context. And when the game was, the game was changed slightly in ways that the system could still play it, it showed no evidence of knowing this strategy. So for example, as this article described, when if they like moved the height of the paddle, the Y coordinate here, or inserted a wall in the middle of the screen, suddenly the strategy of digging a tunnel just totally disappeared. This is exactly the type of thing that highlights this distinction between the way that neural networks, as we currently have them, function, and the way that human beings function. And the challenge to trying to characterize neural networks in terms of knowledge claims, descriptions of what their attitudes are, their beliefs are, their desires are, because their dispositions, their capacities do not seem to be structured in the same way that ours are. If someone knows how to build a wheel, you wouldn't expect that if, like, on a cloudy day, they suddenly forgot how to build the wheel, or in some minimally different context, they would show no awareness of how to build the wheel. We expect that if we see someone do something like come up with a really clever strategy, that the strategy would be kind of resilient across contexts to some degree. So there are tons. This is just one of many examples. I forgot to mention this, that I described these and others in a recent article it hasn't been printed yet, but it's available online, that goes into all of this in more depth, and then builds on the earlier work developed in my dissertation. So for the sake of time, I'll stop it there and turn it over to anyone who has questions or comments or anything. But just right now, thank you everyone for listening. So I'm going to stop share. All right. So from what Amy had told me, this will be the time now for questions and comments. What I see, someone, oh, Diane. Yeah, Diane. It is a way to mimic. Assuming you're talking about neural networks, it does mimic how the brain recognizes images and how we interpret images. But there's also some interesting differences in that, for example, if your visual system worked in the way that a neural network worked, it wouldn't be useful. And it's easy to overlook this. If you have a neural network that can identify which animals are in a picture, it seems like, oh, it can, understand, can identify these different animals. But all it's doing is just converting an image of the animal into the word. So then there's the question of, well, then what would it do with the word? Well, it doesn't do anything. That's all that it does. Mark's question, the brick breaker case. There's a screen in the AI. I'm not sure what you mean by when there is a screen and the AI forgot it.
We can ask questions directly if that's easier.
Oh, yeah.
Yeah, absolutely. Feel free, everyone.
Yeah, I'm just reading over the other ones that have been entered.
I'll just clarify my question if that's okay.
Oh, yeah.
I'm just saying, you mentioned that the AI forgot the strategy when there was an additional element added to the game, like a screen. Is it that it forgot the strategy, or is it just simply no longer optimal?
Oh no, it would still be optimal. So I believe what they did was, like, the system would come up with that strategy and it would consistently apply it, like, game after game, as long as, like, the same number of bricks were there at the beginning. But if you had, like, imagine there was like one additional layer of bricks, like what might happen if you go onto a harder level, there's more bricks that you have to do away with. That kind of change seems trivial, but the system would know it would still be optimal to build a tunnel. I'm assuming. I mean, it's possible that it might not have been. I can't think of how it would not have been with just these subtle changes. It seems like a pretty generally useful strategy. But it only appeared under certain conditions. Does that answer your question? Great. Then Amanda's question. Yes, Amanda, more or less. But the issue is, as some of the like mistakes of these neural networks show, it's kind of like, well, do we want to rely on the system to make the diagnosis, given that it might arbitrarily start making errors? You know, maybe there'll be something that could arise, like the case of the network that was recommending that patients with pneumonia be, you know, set off on their own, and other patients be prioritized for patients with asthma be de-emphasized. You know, you wouldn't know if you're relying on the neural network, you wouldn't know when it's doing something like that. And even with human beings, we can anticipate these things to some extent, right? Like someone, you know, if we've trained someone to do something, some task, and they're doing it for us, we can still say, you know, I think that when they're at work overnight doing this with long hours, they might get drowsy and make a mistake. So we can predict that type of mistake. Whereas with neural networks, the mistakes are often like completely unanticipated. You know, thinking a sign with stickers on it is a refrigerator. Or there's another example of thinking, I think there was like a piece of paper, a yellow piece of paper with black stripes, and the network thought this was a school bus. So the mistakes are kind of random. So it brings up the question of how would we, you know, when would we be willing to trust the network? The case of self-driving cars is kind of instructive here. It's a few like back in 2016, I think it was. You would think from reading the news that this was, you know, we were just on the cusp of self-driving cars being everywhere. But then mistakes like similar to the ones I've described were observed. And then there were all sorts of legal and safety issues that came up.
What other questions do we have for Dr. Byers?
Okay.
Kiba, go ahead.
I'm trying to write, but I can go. Do you? I see the increased use of artificial intelligence. That means there is a crisis in science.
Good. So there is increased use, but it's limited to certain areas. I would say that if I interpret you correct, the crisis is what it's proposed. What people say they would like to do with explainable artificial intelligence, I think, is fundamentally, for like deep reasons, not possible in the immediate future. But it's still, artificial intelligence is still used a lot, but for more kind of trivial purposes, you know, like internet search results, or if you post a picture on Facebook and it will say, you know, is this Sarah? It will make recommendations like that. As opposed to like making a medical, you know, you were just diagnosed with this illness by a computer. That type of more serious decision where there's more at stake, I would expect would take longer to see.
Okay. One more. I was impressed when you were presenting these things. Very, very good. It's new to me. I don't know all the detail, but you mean that when you presented, I have impression that we're going more than psychology itself. Now it's a parapsychology field who's become more important.
I didn't get the last part of what you said.
The parapsychology, like the French call it, beyond the psychology itself, beyond the field become more important.
I don't know. It's kind of a cross-disciplinary thing. I mean, for me, the way I would look at it is even within psychology, it's almost like psychology is more, the differences within the field are almost as significant as from one part of the field to the other.
Okay, very good. But
It was
yeah. Thank you for the presentation. I like it.
Thank you for being in the audience. I appreciate it. On the topic of other disciplines, it was kind of interesting to see I hadn't read research from like on artificial intelligence and computer science before, and it was kind of delightful to see how it's totally unlike the social sciences. Everything is completely open access. You see a paper cited, you can just get it in like 5 seconds. The PDF, no logging in or anything. It was really a kind of, it made it very easy for me to quickly sort of look through all of this other stuff in a foreign field.
Dr. Jankowski, did you have a question?
I was curious about your description of knowledge claims. Would you expect knowledge claims to change as a function of experience or development?
Yeah, that is a great question. So there's so much more I could have gone into with sort of qualifications and things. Part of how the conclusions I reached came up was looking at, in the discourse analysis, like looking at exceptions and trying to understand those exceptions. They often like were the exception that like proved the rule even more strongly. So in the case of, if I'm forgetting the exact phrasing you used, if you were to say that a child knows something, that would be interpreted with respect to, by whoever your audience is, with respect to assumptions about that child. So when researchers report that from doing like looking time studies that 5-month-olds understand number, you wouldn't that wouldn't be taken to mean the same thing that it would if you were saying that about a 7-year-old, or about a philosopher who come up with like a formal theory of number, and understanding number in that sense would mean something very different. So it is that the meaning is definitely dependent on the context where it's applied. I'm not sure if that exactly answers your question.
What other questions do we have? Feel free to enter them in the chat or just to call them out. Dr. Byers, I have a question. Thank you so much for the presentation. As a sociologist, I like to celebrate when computers can't do what we as humans are uniquely able to do. And I think one of those things that perhaps we're uniquely able to do is to think through metaphor. So when you were talking about, this isn't obviously a refrigerator, a human could maybe make a connection between that. So I'm wondering if you have any other thoughts about what you don't think computers could ever really do, or AI could ever really do, and what that means about like the fear that we have in society right now about the ways in which we can be replaced.
Yeah, as some of my students on here may have known already, this is one of my favorite things to talk about. And there's a couple of different, I totally agree with you. And I think there's a lack of appreciation for how much what people do we're just nowhere close to being able to replicate. And there's a couple of different issues. I think one of the main ones is a lot of when we see that a computer or some other artificial intelligence system is doing something, we often sort of over attribute what it's actually doing, forgetting that we know what context we're in. We know what the computer doesn't know the context it's in. It's just doing this thing it was programmed to do. I guess to describe what I'm getting at here, we often forget how we're able to do what we do in a particular context and move from one context to the next and do meaningful things in relation to that. I'm sort of losing myself in this explanation. I think this is like something that's fascinated me for so long. I guess another way to put it would be like you can take a system that translates text. You can put in text, it gives you a translation of the text. I think a lot of people's inclination is to say, oh, wow, yeah, it understands, not only does it understand language, it can translate from one language to another. But what we forget is that it's literally doing nothing else. It can't use that language, it can't use what's said to do anything besides produce a translation. Whereas the fundamental thing that people do is we see things, we hear things, and we act on them, and we respond. The fundamental way that we engage with the world is by responding and doing things with what we interpret. So it's to me, I think it's really one of the most fascinating things in cognitive psychology is the abilities of computers are often to such a great extent an illusion. We're tricked into thinking that it's doing something that it's not. And for my thinking, at least, I think one of the best things you can do if you want to think about how cognitive processes work is try to think about what would I have to do to build a robot that would do this? Or if I was building a robot to do this, what would be the hard parts of doing that? What would it be hard to make the robot do and why? So it's kind of sometimes choosing the wrong metaphor can be really instructive in the long run.
Thank you.
Oh, thank you. Yeah.
Other questions? We have about 5 minutes.
Oh, yes, Jeff.
I was fascinated by the example you gave of the computer that learned to solve that video game about, if I remember correctly, about the 400th iteration. Was that a gradual process, or was it kind of just a very quick change in the way the computer approached it, or how was it described? I forget or did never learn. I don't know. It would be really interesting to look at the dynamics of that change. I don't know, but it's fascinating. One thing kind of along those lines that happens is, I'm forgetting the word that's used for this. Sometimes the system will evolve in a way where it will get kind of close, but it will have evolved in a way where there's it hits a ceiling, or it's kind of like a blind alley, and there's no way with the way that it's set up, there's no way for it to evolve to get any better. So I don't know about the rate of the actual change. I will say, based on what I was saying before, it probably would be kind of delightfully easy to find the answer given how accessible the research is. But yeah, I think that's a great question. Interesting to think about for development.
I don't really have a question, but I would like to make a comment. Thank you for inviting me. And Patrick, it was fascinating to listen to you. It was really an interesting presentation. I thoroughly enjoyed it, and sort of surprised that I was able to follow it as well as I did. So you really did a good job.
Oh, I'm delighted by that, Marshall. I'm delighted to have you in the audience. I'm surprised if it was interesting. I think it's fortunate that Mark and Amy set this up to have a relatively short presentation. If it was longer, there's a lot of details I could have gone into about how I reached the conclusions in the original research. That in my mind, I'm like, well, the audience has to know this for it to make sense. And it, I think, would literally just have bored people to death.
No, I don't think it bored anybody. It was intriguing. It was really interesting. And I hope someday that I can get to see everybody again and that we can discuss it further. It was really interesting, Patrick. Thank you.
I agree, Marshall. Yeah, I'm happy to have and honored to have been able to take the opportunity to sort of come together like this. It's a social event for me, probably more than anyone else. So I appreciate all of you being in the audience.
Well, Dr. Byers, that might be a good note to end on unless we have any other questions. Thank you so much for agreeing to be our first presenter at this symposium. It's something we hope to do at least once a semester moving forward. We'll get to hear about all the interesting research happening across the department and come together socially like this or in person. So, Dr. Jankowski, do you want to offer anything, or Dr. Zeltzer, before we conclude?
Well, I'd like to thank you, Dr. Byers, for presenting. I thought it was a very interesting presentation, interesting talk. It's certainly a very timely and interesting area of investigation, too. And also, thank you, Dr. Traver. Thank you, Dr. Zeltzer. I really appreciate it. And I think we all enjoyed it very much and look forward to the next one. Thank you.
Thank you all.
Thank you.
Thank
Appreciate it.
you. Bye, everyone. Thanks for
Thank you,
coming.
Amy.